recognize the role of the vectors I and j as the simplest what are called basis vectors. And you'll see what the definition of that is in a minute. And we're going to be able to express position vectors, what are called position vectors, in R squared, which is R2. That's the two-dimensional platform that we're going to be using initially in terms of I and j. And we're going to be able to express any vectors in R squared as a position vector in algebraic form as well. Then we're going to be add and subtract these vectors in R2 algebraically. Okay? All right, let's get to it. This is a diagram that illustrates two special unit vectors. They sometimes, when you're seeing this in the University of Waterloo, they call it I hat and j hat. I just call it I and j. The I vector is a vector that runs from the origin along the x-axis to 1. So it's, if you can follow my mouse here, it starts at the origin and is a horizontal line which runs out to 1 on the x-axis. Then there's a vertical line which goes up to 1 on the y-axis, so that'd be up to 0, 1. And these two vectors are referred to, and they're unit vectors because they're 1 unit long. And these two vectors are referred to as our basis vectors because we can use these vectors to create any other vector within 2 space, right? By just simply scaling these vectors. And when I show the video later on, that will hopefully become more obvious. So we can scale I and we can scale j until we get any other vector we like, right? That's what it says right here. Using scalar multiples of I and j, it's possible to use a triangle law, which we talked about before, for addition to write OA. So if you just consider any point in this space right here, I can get from that point to any other point by just simply scaling I and scaling j to get to those 2 points, right? And that's, as I said, using the triangle law. So some scalar multiple of I and some scalar multiple of j, when I add those two together, I can get to any position I want. And this vector OA is what referred to as a position vector. Now, all a position vector is a vector that runs from the origin to some point in space. All right? So as it says here, it's possible to write any vector in 2 spaces, a combination of I and j, when 2 vectors are used to express any other vector in that coordinate system is referred to as basis vectors. Oh, back with you again. I didn't want to share the whole video with you. He goes into something else that we will have to get to eventually, where he uses other vectors apart from those 2 vectors as the basis vectors. But I just wanted you to get a general, I just wanted you to see it in a much better sort of graphic way than I was able to present it to you using the smartboard. But hopefully you get the idea. You have these 2 vectors, the I vector and the j vector. You call it I hat and j hat. And as I said, if you go to the University of Waterloo website, they refer to it in the same way. And if you just simply stretch them out, or you can actually shrink them as well, when you add those 2 together, then you can get any other vector that you want in this thing that we're calling 2 space. So, and we call those position vectors. So any vector that runs from the origin out to some point in space, and that point could be any coordinate that you're accustomed to. So you could figure out that, for instance, this point right here is maybe about, what is that? Maybe about maybe 3 and minus 4 or something like that. Maybe that's what this point is here. So I could scale the I vector by 3 and scale the j vector by minus 4, and I would get to this point down here, and that would be the sum of these 2 vectors. Okay? So as I said before, they call those 2 things the basis vectors. All right, let me move on. So which position vector is represented by 3i minus 7j? Well, I'm taking the I vector and I'm scaling it. I'm going along this line here by 3, and I'm taking the j vector and scaling it by minus 7. So first of all, it's going in the opposite direction. It's going down. So we have one vector along the x-axis and one vector along the y-axis. And when you add these 2 together, it gives you this sum vector right here. So this sum vector that we're looking at, right, this u vector, can actually be seen as being really, and of course, this point that I'm pointing to right here, right, where the head of the vector is a point 3 minus 7. So the way I represent that as a position vector is I use square brackets for that. That's not sort of the convention. Some people, they write them like down. So they put like one number here and they put the other number down here. I've seen it that way before. I just use square brackets to represent my vectors. So that's the way that I'm going to do it. And I'd accept both ways from you, as a matter of fact. So I'm going to go ahead now and I'm going to write this as being 3 comma minus 7. It's really that simple, right? So that vector, which runs from the origin, is called a position vector, is the vector 3 minus 7 because you scale the I vector, which is the 0, the one that goes from 0 to 1, 0. And I've scaled the J vector, which goes from 0 to the point 0, 1. I've scaled them so that they end up forming this U vector right here. The U vector goes from from the origin down to the point 3 minus 7. All right, so that's really all that is. So what position vector is represented by that? Is this position vector right here, 3 comma minus 7. Done. As simple as that. Write the OA vector, excuse me, which runs from O to A as a sum of multiples of I and J. But it's what you think it is, right? I didn't use square brackets here. That's fine. I mean, again, some people even use round brackets as well. So the OA vector, right, the position vector, which runs from O to A, right, can be written as again, this is, I'm going to call this U, as equal to minus 4 times I plus 3 times J. There it is, multiples of I and J. And you thought this was going to be challenging. Not at all, right? I've scaled this vector, the vector that runs in this direction along the x-axis. I've scaled it by a minus 4 scalar, which makes it run in the opposite direction and 4 units long. And then I've also scaled the J vector by 3 units, so it's now going up 3 times as long. When I add those two together, I have a vector which runs from here up to here. Really that simple. Really, really that simple. Okay? Write the position vector OA, and of course I should put a little arrow on top of that. I haven't been doing that, but I should be. Write the position vector OA in algebraic form if OA is 3A minus 2B plus C, where A is this vector using these, again, the basis vectors, B is this, and C is this. Well, if you remember this stuff that we did when we looked at the properties of vectors, it is exactly what you think it is. So my OA vector would be 3 times 2I minus J, right? Minus 2 times 5I plus 2J plus C, which we said was 3I minus 4J. And the rest of this is what you think it is, which is just regular, ordinary algebra. So my OA vector, right, the final position vector, by combining all of these together, would be 6I minus 3J minus 10I minus 4J plus 3I minus 4J. And of course, I would put all of my like terms together. So let's see now, that's minus 4 plus 3, so that's minus I think, minus 4 plus 3, right? Then minus 7 minus 11J. So the final OA vector, the final position vector, is going to be minus 1I minus 11J. Okay? That's it. That's all it is. That's all it is. Now, what about this? If A, that's a point, right? It's not like they're saying OA or anything. A is a point. And you can see on my diagram right here that A is at the point 3, 5, right? B is at the point 1, 8. This is not a position vector. Let me just stress that. That's just a vector running between 2 points. So the U vector right now runs from 3, 5 to 1, 8. Remember, the direction matters. I keep stressing that. So it's not like I'm saying that I'm going from B to A. I'm going from A to B. That's the direction of the vector. It runs from A to B. A is at 3, 5. B is at 1, 8. Tail and head. Tail is the starting point. Head is the ending point of the vector. All right? Sometimes head referred to as tip, by the way. A, B respectively. So A to B. right? Let me put a little arrow on here so that we can see that it's running from A to B. Determine the position. Now remember, the position vector goes from the origin. So as opposed to some vector that's just out there in space on a Cartesian plane, a position vector is one that goes from the origin to some point on the Cartesian plane. Origin meaning 0, 0. To determine the position vector equal to AB, also determine the magnitude of the vector. Okay. So what I did is I drew another vector, excuse me, over here that seems to be looking a lot like this u vector. In fact, I could call this my u vector, right? Because remember, for a vector to be the same, it has the same direction and the same magnitude. But what would this vector be that I'm looking at? Well, could somebody tell me what this u vector is, right? If I were to write this as a position vector, what would that position vector be? And also, what would I say is that vector with its components, meaning the I component and the j component? Can anybody tell me what that vector is? Right, I use my, as I say, I use my square brackets when I'm writing a position vector. So let me turn it over to you and ask you, what is this u? Right, let me make that u look a little bit more clear. It doesn't look like a u right now. So here's my arrow on top, and here's my u, just like this u here. This is a u vector right there. Can anybody tell me what would that position vector, give me the components of that position vector? Okay, so Sarah is saying minus, and Ashwin is saying the same thing. So it's minus 2, excuse me, and positive 3, right? And that could be written in terms of its components as minus 2i plus 3j. But was there a way for me to get that by just simply, so I did that because I could just kind of eyeball it. I wanted a vector that had the same basic direction running from here to here, and I put that vector down here, right? And by the way, I agree with what Sarah and Ashwan just said, 100% agree with them. But is there a generalized formula for finding that AB vector, right? So this is what we're asking about. And also, we didn't get to the point where we found the magnitude of the vector. What is the distance? Let's get to that next. What is this distance? What is this length? What's the magnitude of this vector? In other words, what is this? Is there a way for me to get that distance that we're looking at right now? Can somebody sort of think about that, Pythagoras? Absolutely, Kushi. Absolutely. All right. So if that's the case, could you tell me what that would look like then? Right? You're right. Kushi is right. Using Pythagoras, we could get the length of the vector. Right? Give me the formula for doing that. Right? What would that look like? Kushi is right. Look at what Kushi just said. Kushi said use Pythagoras. Use Pythagoras how to get the distance of that? So it'd be minus 2 squared plus 3 squared. But of course, you know it's the square root of that, correct? It's a square root. So it's a square root of the minus 2 squared plus the 3 squared. And the truth is, we don't really have to put minus 2, right? Because we know that we're really looking at a distance, and that distance is really never negative, right? And plus, when you square it, it's going to become positive anyway. So it looks like the magnitude of this vector would be the square root of 13, if we can all agree on that, right? The minus 2 squared is 4, and the 3 squared is 9. So the magnitude of this u vector seems to be the square root of 13, okay? All right, so that didn't seem too difficult. So they gave us, let me start off with what they gave us. They gave us 2 points, which are just 2 points in space, and then connected them with a vector. And they gave us a direction as going from A to B, right? Tail to head. But now they want a generalized formula for finding AB and the magnitude of AB. So can we generalize that? We kind of eyeball it and said that the vector that represents that is the vector minus 2, 3. But is there a way that we could take 2 points in space? So one point is that, remember, this is the tail of the vector, right? 3, 5. It's the head of the vector, 1, 8. Is there a generalized way for us to come up? Can anybody think of like a formula that we could use to find vector AB? Right? If we have 2 points, right? So we have point A, right? So A has certain coordinates. Let's say X. In fact, I'll give you a clue then. Distance formula. Well, let's get to the vector that represents it first. So let's call this x1, comma y1. This would be the tail of the vector. And then the other point is the point B, which we'll call x2, y2, and that would be the head of the vector, the ending of the vector, right? So what do you think is a generalized formula for finding the vector that runs between A and B? So Richard, that's great for distance, right? But I need remember, when I asked for the vector, you said it was a vector, the position vector, that is, the position vector. You said it was a position vector minus 2, 3. And I agreed with you, because this vector that runs from here to here is a vector that goes this way 2 and this way up 3. So let's see what Sarah is saying. The slope formula. Okay, so slope formula meaning we're going to subtract our x's and subtract our y's. Does it matter what order we, and I agree with you, by the way, it is a slope formula, but does it matter in which direction or in which order we do? Because you notice the slope formula requires a subtraction, right, Sarah? All right, where's everybody else, by the way? Come on, I need some. Yes, thank you, Sarah. But I need everybody else to be chiming in on this, right? We can all agree that to get the slope of a line, we subtract the x and subtract the y's. But does it matter in which order we do that subtraction? Think about what we just did here, right? The tail of the vector was 3, 5. The head of the vector was 1, 8. Tail and head, respectively. We ended up with the minus 2, 3 line. Does it matter? Ariana says no, and Ashvan says no. Does everybody agree with no, that it doesn't matter in which order we do that subtraction? Alexander says yes, as in you agree with them or you think the order matters. I want to be clear on what you're saying. Does the order matter? You agree with what? What do you agree with? Agree with no. The order does not matter. It doesn't matter. I see. So everybody is saying that the order doesn't matter when we're doing this. Is that what the consensus is? Is there anybody who disagrees with that? Nobody wants to get on the train that says, no, the order has to matter. Everybody thinks the order doesn't matter. I'm just trying to get a sense from the class here, because everybody is agreeing with Shira and, let's see, slope formula, and Ariana and Ashford and all those people said doesn't matter. The fact is that it does, unfortunately. If it was that that the direction didn't matter, then it wouldn't. The slope, you could figure it out by taking either point and subtracting it. But it does. So Thomas, yes, it does, right? If you were to subtract it one way, the vector would go in one direction. It would be the same line. Let me just be something. I just want to be clear on this. The same line would result. So this line that goes from here to here, the same line goes from here to here. But the direction actually does matter. So I want you to look at the answers that we got, which was minus 2 and 3 here, right, for the position vector, and ask yourself, is it tail minus head or head minus tail that we used to get the answer just now? Tail minus head or head minus tail? Look at the answer again that we got. It was 3, 5, and 1, 8. We ended up with minus 2, 3, right? Which goes from here up to here, right? So it is in fact head minus tail. So here's our general formula that we're going to be using. The general formula would be, it would be the x head minus the x tail, comma, the y head minus the y tail. Obviously, I'm using abbreviations here. rather than writing it all out, it's head minus tail. The x's minus the two x's, but the head first minus the tail, which is why we have, if you go back up and look at what we have here, that's why it's 1 minus 3, which gives us minus 2. That's why it's 8 minus 5, which gives us the 3. All right, can you explain why it's head minus tail? I sure can, Ashvan. Okay, now if we're just talking about slope, Ashvan, right? In fact, let me add a page in here. And let me just put a little, let me put a grid in here to show you why it makes a difference here. So Cartesian grid. All right. So let's say that I put 2 points on here, right? And just measure the slope between them. So this point here and maybe this point right here. And let's drop a line in between those 2 points. And thanks for the question, by the way. Just an arbitrary line, right? Oh, and those 2 points on the line, by the way, I'll just label those 2 points. This is the point minus 4, 1. And this is the point 2, 3. All right. So let's think about that now. No, we don't care about direction right now. This is just a line. Right? I'm not asking you in terms of vectors. This is just a line that goes from minus 4, 1 to 2, 3. That's all it is. Well, for me to find the slope of this line, Ashvan, what I would do is I would say, I would take the minus, remember, it's minus 4 minus 2 over 1 minus 3. Are you agreeing with me on that, Ashvan, for finding the slope of this line? Does that make sense so far? I'm subtracting the two x's, minus 4 minus 2. That's going to give me, what's that, minus 6 over minus 2, which is therefore 3. So the slope of this line is, that doesn't look like 3. Something is wrong. It's y over x. Nobody said anything to me. Nobody, y'all just sat there and didn't say anything to me. It's actually the other way around. This is a slope of 1 over 3. So let me, all right, I'm just going to erase all this garbage here. Nobody said anything to me. I'll just erase all of it. It's the y over the x, folks. You all know that. And you let me just write that down and said nothing. Okay, so let's try this again then. So let's go 1 minus 3, right? So that y minus that y. And let's take the, let's see now, what am I doing here now? X's. So I'm going to do it in the same order. So it would be minus 4 minus 2. Did I do that right? I did that right, did I? Minus 4 minus 2. Right, okay, I think that's right. So 1 minus 3 is minus 2. And this is minus 6 on the bottom. So this would be 1 over 3. Okay? No. If I did this the other way, Ashvan, which is to say, if I were to take 3 minus 1, right? So taking this one first and then subtracting this one, I put 3 minus 1. Then I'm going to put 2 minus minus 4. I'm going to get on top 2 over 6, which is still 1 over 3. So if I don't care about what direction this goes in, then I would say that it doesn't really matter what order I do this. The slope of this line, if I put another line down here which had another slope, let's pick a line here. And then let's see now. So go up 2 and across 6 to take us about here. That's another line that has the same slope. And this has the same slope. So it's almost as if they were the same line. But because we're talking about vectors, we have to make sure that we're heading in a particular direction. So in this case, let's say this was a vector running this way. Now I'm actually forced to look at it in terms of tail minus head and not head minus tail, because although I get the same slope, I wouldn't get the same direction. The direction, remember, the direction vector for this one has to go like from here to here. If I were to subtract the other way, it's going to go like from here to here. Although those two lines have the same slope and they're both starting from the origin, they're going to go in opposite directions. Does that kind of make sense to you now, Ashvan? Just want to be sure. Right? They're going to have the same slope, but they're running in opposite directions. Okay? So the order that you subtract it absolutely matters when you're doing a vector. And it's head minus tail. So whatever the head is, the head coordinates, you find those and you subtract your tail coordinates, and then you can express it that way. Okay, this is when you're dealing with slope. When we're dealing with what we're dealing with here before, since we want to put the components x first and y second, it doesn't really matter whether you put y over x, because it's not like you're trying to get a fraction here, right? So I get my x components and subtract them, but it's head minus tail, which is what we did, 1 minus 3. Take my tail components and subtract them. So that's 8 minus 5, which is a 3. Then I can express it also in terms of basis vectors, minus 2i plus 3j. Then I can also find what the magnitude is, and that's what we did here. Okay, so this is the generalized formula that you saw me write down here. X would be, the x component would be xh, x head, minus x tail. The y component would be y head minus y tail. Now to get the magnitude, what would be the general formula for that? Okay, you also said it was a distance formula. Does the order in which I subtract them this time matter? Right? It's the square root of something. Right? Does it matter this time when I'm trying to find the magnitude of this vector, this position vector? Absolutely not, doesn't matter. Does not matter, right? So I can put the, whatever this difference is here, this xh minus xt, I'm going to square that. So again, right here, it doesn't matter because I'm going to square it anyway. Plus, I'm going to take the difference between the y's. So that would be yh minus, that's an h, not a very good looking h, but it's an h, minus yt, and square it. But I could just as easily switch these around. Doesn't matter, right? You want to put the tail first, you want to put the head first, I don't care, right? Because when you're doing the distance, it's the distance between 2 points squared for the x's, and the same thing for the y's, and you take the square root of that after you sum them. Does not matter this time. So it matters the order in which you do your subtraction for the position vector. It does not matter for when you're trying to get the magnitude. Okay? All right. Move this along, folks. Let's move this along. So, given P equals 2i minus 5j, Q is minus 3i plus j, and R is I plus 2j, find the magnitude of 3p minus q plus 2r. Well, that's not hard at all, right? And I think most of you will be able to do this without me even showing it to you. So let's just see now. 3 times these two basis vectors, that's 2i minus 5j, minus q, and q is minus 3i plus j, plus 2r, so that's 2 times I plus 2j. And of course, we just have to do a little math here. So that would be 6i minus 15j. Folks, if I make a mistake, you know that you're welcome to stop me. Plus 3i minus j plus 2i plus 4j. I think I did that right. I think 2i. Okay. Let's add up let's just put our like terms together now. 6 plus 3 is 9, plus 2 is 11i. So minus 15 minus 16 plus 4 minus 12j. Okay, so these represent our components that give us a basis vector. So I don't have numbers to subtract or anything. So how am I supposed to get the magnitude of this? Any ideas as to how I'm going to get the magnitude of this? Remember, this is a position vector. This represents a position vector. This vector runs from the origin and is scaled along the x-axis by 11 and is scaled along the y-axis by minus 12. So what do you think, folks? What would this magnitude of this, let's call this vector u, right? So what we're trying to do is find this, 11i minus 12j. We're trying to find that magnitude. What is that equal to? Pythagorean theorem? Okay, good. All right, tell me how to set that up, Adam. What do I do to set that up? I agree with you. It's kind of the distance formula, but they didn't give me 2 points here. So think of it this way: one of the points is 0, 0. There's a position vector. So this vector that we're talking about right now, the tail of this vector is at the origin, because that's what position vectors are. And the head of the vector, well, you think about that, and then you tell me it's a root of correct. It's the square root of 11 squared plus 12 squared. It's as easy as that. It is as easy as that. You just simply take the two components, you square them, you add them to get square. You square them, you add them together, you get your answer. So let me just see if I can do this mentally. That's 121 plus 144. Look at me, mom. No calculator. Is equal to the square root of 246, I think. No, that's not right. 265. Sorry, don't look at that, folks. Don't look at that. That's just ignore that. 265. Sure enough about no calculator and getting it wrong. 265. Thank you very much. Yes. Thank you, Adam. Okay, so there you go. As simple as that. Really as simple as that. Okay, so that's it for R squared. That wasn't too hard. I can write a two-space vector as a combination of I and j. I can write a vector in two space as a position vector in algebraic form. I can find the magnitude of any vector in two space. Let's move along to three space. So move out of two-dimensional space and move into three-dimensional space. So apart from the x and the y-axis, which you're accustomed to, you've seen x and y-axis all your life from grade, probably before high school. I'm going to recognize the role of three vectors now, I, j, and k, as the simplest basis vectors for R3. I'm going to be able to express position vectors in R3 in terms of I, j, and k. I'm going to be able to express any vector in R3 as a position vector in algebraic form, add and subtract vectors in R3 algebraic. And if you think of what we just did in R2, R3 is going to make a lot of sense. Okay? So as I'm doing this, I want you to think sort of the way you saw that three-dimensional x, y, and z scale, all right? Or axes, I should say. So this diagram illustrates three special vectors, the I, j, and k vector. The I vector is the one that's running along the x-axis. Think of the x-axis as coming out of the board towards you here, right? I think that's what the x-axis is, the one that's coming out of the board towards you. And the side that's in your face is the positive side, and the side that's in the back is the negative side of the x-axis. The y-axis is right and left. Okay, think of the right of it as being the positive side and think of the left of it as being the negative side. The z-axis is the one that goes up and down, vertical. The top of it is positive and the bottom of it is negative. Again, you got to think three-dimensional at this point in time, right? And the three vectors that we're talking about are kind of the same three vectors as before, except we add in a third dimension now. So the I vector is still the one that runs along the x-axis, and it's 1, 0, 0. Now we have triples to represent each vector. So there's an x coordinate, there's a y coordinate, and the third one is a z coordinate. So this 1, 0, 0 is the one that runs 1 along the x-axis, 0 along the y, and 0 along the z. Right? So try to think three-dimensionally now. The j vector is the one that is on the y-axis. It's at 1 on the y-axis, 0 on the x, and 0 on the z. The one that's running up here is 1 on the z-axis, 0 on the x, 0 on the y. But the principle is still the same. We can add scalar multiples of these vectors, the I, j, and k vector, right? And we can create a new vector, and again, a position vector that runs from the origin to somewhere in space. So look at this ABC point right here. This is the point A along the x, B along the y, C along the z. And if I were to scale my I, j, and k vector, I could end up at this point right here, and there could be a vector running from the origin out to that point. So it's possible to write a three space as a combination of I, j, and k. When three vectors are used to express in a 3D, referred to as basis vectors again. So no real difference between what we're doing now and the one that we did before with 2 space, except we're adding that third dimension to it. All right. So vector OA connects the point 0, 0, 0, the origin, and the point 3, minus 1, 2. Write OA in 2 different ways. So one way that we could write OA, and it's vector OA, by the way. One way that we could write the vector OA is to write it as the sum of 3 vectors. And it's exactly what you think I'm saying. It could be 3i minus 4j plus 2k. So let me take you back again. Right? When you have the I vector is the one on the x-axis, the j vector is one on the y-axis, and the k vector is the one on the z-axis. So these represent, you're going from 0, 0 to 3 minus 1, 2. So it means that it's 3 along the I minus, where's minus 4 coming from? Where did that come from? Hang on, folks. I'm not sure. Okay, Kashaf. I don't know where minus 4 came from, folks. I don't know, that just popped into my head. I'll erase it. All right. So 3i minus j, oh, sorry. 3i minus j, yeah, minus j plus 2k. Okay, so that makes sense. The other way that we could write it is as a position vector, which is to say 3 minus 1, 2. Right? And again, I use my square brackets to represent the fact that it's a vector, a position vector running from the origin out to this point A. Right? So there's a point. One point is O, one point is A, and O to A goes 3 minus 1, 2. All right, let's try this now. Given the points B, C, and D, write a single vector to represent OB plus OC minus OD. Okay, so let me turn that over to you. What do you think that looks like if I'm adding these together? These are all basically position vectors. OB means I'm running from O to B, right? O being the origin, by the way. OC means I'm running from O to C, and OD means I'm running from O to D, but I'm going in the opposite direction. And here are the points. 1 minus 2, 3. So that's a point. C is 3, 0, minus 1. And D is 4 minus 2, 3. Those are my points. So write a single vector to represent the sum and difference of all of these vectors. If I just gave that to you right now, and it's probably easier than you probably thought it would be. So it's almost an obvious answer. How do you think we would actually come up with the answer? All right, let me ask you what you think. So here's one point, here's another point, here's a third point. How do you think I'd write the OB vector plus the OC vector minus the OD vector? Come on, folks. I think you can do this. How do you think I would write the single vector to represent the sum and difference of those vectors? I'm going to wait for somebody to tell me, seriously, because I want to hear some feedback from you. What do you think I would do to get, if they're all position vectors? My guess is Pythagoras' theorem again, Adam says, but I'm not sure. Pythagoras' theorem, I would agree with you if I was trying to find a distance, but I'm not trying to find a distance this time. What I'm trying to find is a vector. You see what I'm saying? We'll get to the distance later. Right now, all we're really trying to find is one vector to represent, it says right here, a single vector to represent the vector OB, OC minus the OD vector, right? So I'm not even going to try to put this on a grid, because if I try to draw something in 3 space right now, you would all sort of be on the floor laughing, just rolling over it laughing. And I'm not going to embarrass myself by even trying to do that. I could try putting it into the GeoGebra to show that to you, and maybe on another occasion I will. But it's easier than you think it is. So let me throw it back over to you again. Adam at least had an answer. Where's everybody else? Right? What do you think I need to do to add those vectors together? Now remember, each of those vectors is a position vector running from the origin to that point, right? So it's like saying OB is running from 0, 0, 0 to 1 minus 2, 3. OC is running from sub in, okay, let's see now. Sub in with I, J, and K. Okay. All right. But I'm still kind of curious as to why I'm not hearing from other people. This is not what I want. Okay. Find OBOC, would you like we found in OA in previous part? Okay. So you're saying, okay, Kushi and Adam, it looks like those are the two people in the class too. Hang on. You know what? Let me do a little roll call because I'm just kind of worried that some people are falling asleep here and we need everybody to be on board with what we're doing. Fernando, where are you? Are you there? Tash says, I'm here, just confused. Okay, and that's fair. That's fair. And Anika's okay. All right, okay. Okay. So is it when we got to this point that you got confused? Or let me go back and see if this page made sense to you. All right. So Alexander says he's here. Good. Alicia is confused. Okay. Can I go back then? Let me just back up a little bit. Let me go back to this page a bit here. Does this page make sense to you? Right? That we said that we can create a vector by simply adding the basis vectors for each of these, right? Okay, does that make sense to everybody? I want to make sure. Can I explain again? I sure can, Ariana. I sure can. So when we're doing this in two space, we said that we could create any vector, right? Any position vector in two space by just adding scales of the basis vectors, the I vector and the J vector. That's what we said. Did that make sense, first of all, right? That I could scale any two vectors to create any position vector in two space. Okay, good. The same thing is true for three space. All three spaces is a three-dimensional representation of a vector. So what we're now doing, excuse me, is we are saying that, let's say, for instance, this point here is ABC, right? I could create the ABC vector by scaling the I vector by some number, the J vector by some number, and the K vector by some number, and then adding those three vectors together. Okay? Does that make sense so far? Right? I'm just I was taking two vectors before, but now I'm taking three because we have three basis vectors to consider. And when we scale those three vectors and add them together, we'll get a vector that runs from here to here. I don't know how long it would take me to put that together in the GeoGebra. So I'm going to try to see if I can press on with this for now. Right? So all right, let's do this then. Let's go back to this page here. Right? And let's say the vector is a vector, the point 1 minus 2, 3. Let's use that. Let's see what Vanessa is saying here. Is it 1i minus 2j minus 3k plus, of course it is. It absolutely is. It absolutely is, Vanessa. You're absolutely right. Thank you very much for pointing that out. But and look at what Vanessa is saying there. But let me just kind of point this out. I'll do one at a time. O to B, my difficulty is trying to draw this for you, and I'm going to try to avoid drawing it for you. So from O is a point. Let me tell you what O is. O is a point 0, 0, 0. Right? That's what O is. B is the point 1 minus 2 minus 3. Okay? Is it that simple? Yes, Anika, it's that simple. It is that simple. Anyway, let me go back to this first though. 0, 0, 0 is the origin, right? It has three components to it, and they're all 0. B is the point, not the vector, is the point 1 minus 2 minus 3. So if I wanted to get from O to B, right? If I want to put a vector that runs from O to B, would you agree with me? I just need an example. Thanks. Okay, right. Would you agree with me that to go from O to B means taking each of these components? I'm going to take one. This is the head of the vector here, because I'm going from O to B. That's what OB means. I'm going from O to B. This is the head, this is the tail. Right? So that means I'm going to get what we said in the R2 was I'm going to take each component of the head, subtract the tail. So it's going to be 1 minus 0, minus 2 minus 0, and minus 3. So because I'm minusing the tail, which is 0, 0, 0, it means that the OB vector can be written as simply 1i minus 2j minus 3k. Isn't that what the OB vector really is? That's the OB vector right there, right? From O to B would be 1i minus 2j minus 3k. The OC vector is what you think it is. The OC vector would be 3i minus k. Okay, see what I did there? I left out the thing in the middle because that's going to be 0 times j, which means that it's no longer there. Then I have the minus k on the end. And then the OD vector, now remember, if you're minusing the OD vector, it's like going the opposite direction. So the OD vector, right? The OD vector would normally be 4i minus 2j plus 3k. But if I'm going to go, if I want to be able to add this vector, then I could do the DO vector instead, which we talked about before. And so that's the OD vector, and the DO vector would be equal to the opposite direction. Put a minus in front. So it would, instead of going from D to O, it would be minus 4i plus 2j minus 3k. That's the DO vector, which is the same thing as the OD vector. So sorry, it's the same thing. So I'm saying that wrong. The OD vector runs this way: 4 minus 2, 3. The DO vector, which is so I can add these three together. I can add together this. I'll circle them. I can take this and I can add it to this, and I can add it to this. This is the opposite, which is how do we get OC? OC. How do I get OC? Oh, okay. So the C vector is at 3, the C point, I should say, is at 3, 0, minus 1. Okay, Ariana? So it means that I've scaled it through along the x-axis. I did not move along the y-axis at all, so there is no need for a j. And then I took the j vector and I made it become the 0 vector. I should put it that way. All right, and then the k vector was scaled to become minus 1. So here it is. It's 3i minus k. That's all it is. That's where OC comes from. Does that make sense to you, Ariana? Okay, so now I'm just going to add these three components together. The OB, the OC, and I'm going to call it the DO vector because I took the OD vector and I turn it in the opposite direction. I'm going to add these three together. So what I'm going to have is, right, so let's leave this out of it for now, right, because I took another vector to represent that. I'm going to add down, right? So what I'm looking for now is a single vector, the single vector that represents the sum and difference. So that's going to be equal to, so 1 plus 3 is 4, and I'm adding that to minus 4. That means that it's going to be the 0i vector, and that's going to make that disappear in a minute. This is minus 3 plus 2, so minus j vector. And then let's just see now. I did something wrong. No, I'm putting in a k vector and some. No, that's wrong. That's wrong. That's wrong. That's wrong. Sorry. There is no j here. This one doesn't have a j in it at all. So let me erase that. Sorry. So it's minus 2j plus 2j, which means I have plus 0j again. Oh, sorry. And then the minus 3k would give me minus 6k. I think I did that right. We should probably double check that again. So the single vector, and I need to double check my work. The single vector is the minus 6k vector. All right, let me double check that. Let me see if I did everything right. So 1 plus 3, and then minus the 4 gives me 0. Minus 2 plus 2. Oh, hold on. 1 plus 3 minus 4, that's 0. Minus 2, and then we're going to add a 2, that gives you 0 as well. And then minus 3 gives you minus 6. Yes, 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 yes. So the single vector minus 7k. Yes, 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 you're right, Fernando and Ashran. You both got minus 6k. So the single vector, right, which represents all of this, could be written as 0, 0, minus 6. Okay? Minus 7, sorry, minus 7. Oh, you got minus 7. Oh, hold on. How am I getting minus 6 then? How am I getting minus 6? How am I getting minus 6? Minus 3. Minus 3 is minus 6. How are you getting that? How are you getting minus 7? Sorry. How do you get minus 7? Did I do something wrong? Oh, there's a minus 1 here as well. Ah, yes, you're right. You're right. You're right. Okay, sorry, sorry. You're right. I'm wrong. Let me fix it. You're absolutely right, and I'm wrong. Yes, yes, yes. Okay. I forgot the minus 1. Yes, Ashwan. Yes, I forgot to bring that minus 1 in. Yes, you're absolutely correct. So minus 3 minus 1 is minus 4, and then we have to minus another 3 from the minus 7k. Yes, yes, yes. See how easy that was, folks? And you all thought that was going to be difficult, right? Yeah, no, you should add the minus 1. I just messed up. All right. So yes, so the vector that I'm talking about is a vector that basically lies on the z-axis. It's just 7 up, 7 down, sorry, on the z-axis is what you get when you put these 3 vectors together. Okay. All right. So that was easier than you guys thought it was. You probably thought it was going to be harder than that. Okay. Let's try this. Let's see if we can finish this up before the end of the class. I'm going to actually, and you're going to be disappointed to hear this, I'm going to actually have to hold off on the homework for now because I didn't get as far as I wanted to get today. So consider the homework postpone. I know, Fernando. I know. I'm gonna make it up to you. Trust me, okay? So this is just a delay. This is not completed putting it up. Anyway, let's get to number 3. Given that the vector has an initial point at minus 2, 1, and 4, an ending point at 5, minus 3, minus 3, what position vector is equivalent to PQ, right? So remember, so sad. So remember now, initial point means this is the tail, and this is the head, right? So what position vector is equivalent to P to Q? So I'm going from P, that's why P is the tail, and Q is the head, all right? So tell me, folks, I am trusting you that you know this. You know this. What would the position vector be that runs from P to Q? All right? Tell me how I'm going to do that. I want the PQ vector. Think about how we did this in 2 space. Because it's exactly the same thing. Right? It's exactly the same thing. We're going to do it in 3 space. Head minus tail. Right? So starting off, give me the first component of this new vector. Right? Give me the first component of this new vector. Help me out here. Remember, head minus tail. 5 minus 2, though. It's minus 2, right? So that would be, what would that be then? 7. Thanks, Alexander. And give me the other components now. Give me the y component. Is that 4 or minus 4? What is that you have there? I'm going to agree with minus 4. And the z component. The z component. What's the z component? Minus 7. Again, the order matters. Okay? If you had switched these around, then that would be the q to p vector. What we want is the p to q vector. And that's why we're taking the head minus the tail. 5 minus 2, 1, sorry, minus 3 minus 1, and minus 3 minus 4. Okay? How about the magnitude of this vector? What is the magnitude? How long is this vector? Right? And again, it's what you think. Okay? I'm assuring you it's exactly what you're thinking right now it is. Right? What do you think I would do to get the magnitude of this vector? Right? Just think about what we did in 2 space, because it's the same thing extended to 3 space. How long is this vector? Right? So what is the P to Q vector? Distance. Distance. Okay, distance formula. Tell me, set it up. What is it going to look like? Is equal to what? The square root of 7 squared. Exactly. Exactly. It's a square root of. You know what? In this case, the sign of these numbers doesn't matter, right? I'm just going to put 7 squared. I mean, I could put minus 7 squared if you like. If that's, that makes it work for you. Actually, it's not minus 7 at all. Hold on. Sorry, that's not true at all. It's positive 7 anyway. So positive 7 squared plus, I could put minus 4 if you like, squared. Doesn't really matter though, whether it's positive or negative. Plus minus 7 squared. And I see an answer over there from Fernando already. So I'm guessing she got, what is that, 49 plus 16 plus another 49. Oh, sorry. So I'm thinking you're right, 114. Absolutely. Yeah. Okay. So it's a square root of 114. Really as easy as that. Let's see if there's something else we need to work on here. Okay, let's see if we can power through some of these fairly quickly then. Okay, so G, excuse me, is at 3, 1, minus 5, right? H is at minus 1, 0, minus 4. And these are points. These are not vectors, right? These are all points in 3 space. Determine each of the following. So these are now the vectors. All right, I'm just putting quick arrows on there. See if we can do this quickly. So what's the OG vector? Right? What would be considered the OG vector? OG sounds like, anyway, never mind. What would be the OG vector? All right? And OG doesn't stand for anything else except what we're dealing with in math here. What's the OG vector here, folks? Right? Remember, the G point is at, there you go, right? You can express it using the basis vectors. So it would be 3i plus j minus 5k. Or if you want to write it with the brackets, it would be just 3, 1, minus 5. The same thing would work for the OH vector. So I'm actually going to skip that, right, in the interest of time, and go straight over to the, thank you, Richard, and thank you, Kushi. Go over to the GH vector, and then after we do that, we'll stop. All right, we'll stop there for the day. I know we're not going to finish everything I had planned, but that, that's fine. What's the GH vector, folks? Give me the GH vector. All right? The quicker we can get that is the quicker I'll shut this thing down and we'll move on. Okay, I'll just ask for one more thing. I'm going to ask for the HG vector after that, and then we're done. What's the GH vector? The G to H. Give me the components of the GH vector. Anybody? All right, there's a whole class of, 28 students, and I keep hearing from the same people. Okay, so is it just minus 1? That's the answer, Kushi? Or is it minus, oh, you give me 3 different, I got you. Right? So you're saying if I'm going from G to H, remember that means that H is the head and G is the tail, right? So you're saying I'm going to start off at minus 4. And then my next component would be minus 1. Nice. And then my next component would be, let's see, and 1 at the end and 1 at the end. And again, that can, 1 is at the end because you're taking minus 4 plus 5. Minus 4 minus 5 minus 5 is plus 5. And again, you can write that with components. What would the difference be for the HG vector, right? Without you having to go through a lot of work, how would I get the HG vector? Right? Can anybody tell me that quickly? What's the HG? So this is the HG vector right here. We did the GH. What's the HG? Just flip the side. Look at that. Cushy. Wonderful. So in other words, we just flip the signs. So this would be 4, 1, minus 1. Right? If you have a vector going one way, you can just multiply that vector by a scalar of minus 1 to make it go the other way. It's really that simple. So all the signs just basically get flipped. All right. As much as I know you really, really want to dive into that homework, folks, I will leave it on that note. And tomorrow we'll finish this up and give you all you need to be able to tackle that homework. So as of now, you have no homework tonight, but tomorrow we definitely will have homework. You can look at it, and maybe if you want to jump ahead a little bit because we haven't really touched it yet, you can have a look at it. But you're not. It's not going to be due right away. All right. I think that puts a cap on that. And folks, you have a good evening and or afternoon or whatever. And we'll see you tomorrow. You take care. Bye.